Hello, today we'll be solving the problem for video presentation 1. The problem states that a potential flow against a flat plane can be described by the stream function psi equals AXY, where A is a constant. We're given a diagram that illustrates this. We have point O, and our flow. Obviously, this is our flat plane, X and Y, our Cartesian coordinates. Then the problem states that by adding a source of strength at O, the stagnation point against a flat plane with a bump is obtained. So this also gives us a new diagram that I'm going to illustrate here with a bump with a particular height h. The question then asks us, determine the relationship between the bump height, the constant A, and the source of strength. So as we can see here, we're going to need to manipulate our equation to include the height. To include the source of strength that we included with the bump that has height. So psi equals AX plus M. And we're going to want this to be in terms of theta for our velocity equations, divided by 2 pi. Also, we want this equation to be in polar coordinates, like I said, so we can take our derivatives with our velocity equations. So the stagnation point here, where the fluid velocity is 0, is going to be right here. So in Cartesian form, that's x equals 0 and y equals h. In polar form, that's going to be 2, and r is going to be our h. So now we can write down our velocity equations, which are defined as Vr equals 1 over r d psi over d theta in respect to theta. So taking the derivative, I did not write our equation in polar form. Let me do that real quick. So that's going to be a over 2 r squared sine 2 theta plus. So now we have this equation written out so we can take our derivative. All right, so that's going to be, once we take our derivative, AR cosine 2 theta plus M, theta drops from our derivative, over 2 pi, and we're dividing by r. Now for the theta, the equation is defined as negative d psi over d theta. And that's going to become AR sine 2 theta. And yeah, that's going to go away with respect. Oh, yeah, this should be, sorry, I goofed on this equation. This should be actually respect to r, so that, yeah, so that the m goes away. And this is our derivative. All right, moving on. So this is in respect to r, not theta. My mistake. So we know our stagnation point is here. So plugging this into v theta, we see that pi over 2, that sine of pi will be 0. So v theta will be 0. So for that to be our stagnation point, we know that we need VR also to be 0. So just equating this equation to 0 and plugging in theta and r, we get AH sine, oh, excuse me, wrong. Yeah, I can actually, here, I can demonstrate this is 0 while I'm at it. This is sine of 2 pi, that's 0. Okay, VR is going to be AH cosine plus m over 2 pi h. So we just plugged in that, and this is equal to 0, as I stated, because our stagnation point will have a velocity of 0 in the r direction and the theta direction, or xy in Cartesian form. So this is going to equal -1. So we have 0 equals negative AH plus m over 2 pi h. So this equation right here defines what we're looking for, which is the relationship between the height, the constant a, and the source of strength. So redefining this, we see AH equals m over 2 pi h. And from there, we can see h squared equals m over 2 pi a. And this is our relationship that we are looking to find. So h squared equals the source of strength, the height squared equals the source of strength divided by 2 pi times our constant a. This has been video presentation 1. Hope you enjoyed it. Thank you.